This conference will now be recorded.
Hello everyone. So last class we ended with Fullerene and we have seen the structural features and also the other aspects of Fullerene, and only the application part of Fullerene was left, so we will finish that. So after Fullerene, which is one of the allotrope of carbon, there is some more allotropes of carbons we will also discuss, and once all the allotropes we have finished discuss, next we will start some important compounds of carbon and silicon. Fine. And under important compounds of carbon, we have two compounds. One is carbon monoxide and another one is carbon dioxide. So in today's class, we will discuss all this, that is rest of the allotropes and carbon monoxide, carbon dioxide and related problems. Here fullerene is used, as you can see, as conductor, then as absorbent for gases, also lubricant, cosmetic products, biochemical application, and sometimes in making carbon nanotubes based fabric and fibers. So carbon nanotube is basically another allotrope of carbon. Okay, so after fullerene we'll also see the rest of the allotrope. So these are the application parts. Now one important point that we have to remember, until now we have seen diamond, then graphite and fluorine, these three. So all these three are under crystalline type of allotropes. We know there are crystalline allotropes, there are also amorphous allotropes. Now diamond, graphite, fullerene, all are basically crystalline. Now among these three, which one should be considered thermodynamically most stable allotrope? That is actually graphite. It is true that all of these are carbon. Chemically, if we consider, that is the chemical properties, if we consider, it is true that all of them are carbon. But in thermodynamic calculations, which of these forms should be considered as the most stable allotrope of carbon? And that answer of this question is graphite. So that is why when we consider enthalpy of formation of carbon, we know that enthalpy of formation for any element, that is their normal state. Under standard condition, what is the normal state? If we consider, just take oxygen. Under normal condition, it is gas. It is not solid, right? Similarly, nitrogen, that is also gas. So just like that, when we consider enthalpy of formation for any element, so carbon is also element, but there are different forms. But which element will be considered during the calculation or any other related problems? When we need enthalpy of formation of carbon, enthalpy of formation of carbon I am talking about, then which of the form of carbon we should consider? The answer is graphite. Enthalpy of formation, which is denoted like this, and as graphite is considered, that means it will be considered as 0, because for any element enthalpy of formation is 0. Now for carbon, among all these forms, only for graphite, this del HF not value, it is considered 0. But if you consider the same value for the other two crystalline allotropes of carbon, then del HF not value for diamond and fullerene, as you can see, not any fullerene, it is C60 fullerene, because there are different types of fullerene, but we are just focusing on C60. So for diamond, del HF not value is 1.90 kilojoule per mole, and for fullerene it is very high, 38.1 kilojoule per mole. But for graphite it is considered as 0. So whenever you have any, you are solving any problem regarding enthalpy of formation of carbon where this term is needed, then the 0 value you can consider only for carbon. But if it is given in the problem that enthalpy of formation of diamond or enthalpy of formation of fullerene or any other allotrope, then you should not consider del H F not value as 0. It is only true for graphite. So why it is like that? It is because thermodynamically it is the most stable form. Fine. Now we have a question here which is based on fullerene. The incorrect statement regarding the structure of C60 we have to find. Now this is fullerene. Here the first statement is saying that the 6-membered rings are fused to both 6 and 5-membered rings. we know that there is both 6-membered ring and there is also some 5-membered rings present in the fullerene, the structure we have seen in the last class. So 6-membered rings are, that is how they are fused. If we know that, then only we can answer this question. Now here we have this structure. Now look at this structure very carefully. This is 5-membered ring, right? Now surrounding 5-membered ring, there is only 6-membered ring, isn't it? So it means that 6-membered rings are surrounded by both 5-membered as well as 6-membered. Because if you look at 6-membered, see, I'm just focusing on 6-membered. So this is a 6-member, right? Now surrounding this 6-membered, you can see there is also a 5-membered, and in other side there is 6-membered. That means 6-membered ring, when you are focusing, it is fused by both 6 as well as 5. But if you are considering 5-membered rings, then it is surrounded only by 6-membered rings. Okay. So the first statement is saying that 6-membered rings are fused to both 6 and 5. This is actually true statement, right? Second statement, each carbon atom forms 3 sigma bonds. Now look at the structure again. If you focus on any carbon, then surrounding this carbon, this is one sigma bond, another sigma bond, third sigma bond. This is actually pi bond. So 3 sigma bonds are present for each carbon. This is also true. Third statement, the 5-membered rings are fused only to 6-membered rings. This is also true. If you focus on this part, you will understand this. Only one statement is left. It is saying that there is total 12 6-membered ring and 24 is the number of total 5-membered rings. But this is actually not correct. Total number of 6-membered rings is basically 20. And total number of 5-membered rings is basically 12 only. So this statement is false. That means this should be our correct answer, because it is asking the incorrect statement regarding the structure of C60. So the incorrect statement is the last statement. Okay. Total number of 6-membered rings, the value that is given, that is not true, and also not true for 5-membered rings. It should be 20 and 12 for 6 and 5 respectively. After finishing fullerene, so total 3 crystalline allotropes we have seen. First diamond, then graphite, then fullerene. Now the fourth crystalline form is carbon nanotube. This is also crystalline, okay? And these two, they are amorphous. So CNT, which is short form of carbon nanotubes. So this is plural. It is not a single form. Just like fullerenes, remember we never say fullerene, it is fullerenes, because there are so many different types of fullerene, C60, C70. So just like that, CNT also, it is CNTs, that means carbon nanotubes. So this is another recently discovered allotropes, because diamond, graphite, these are very fast discovered allotropes, but this one is recently discovered allotropes. So their structure is, there is some similarity. They have graphite-like tubes, but see, the endings are like fullerene. Details will not go, that is not for, not required for this level, but we will just have some primary idea. So there is some similarity with graphite and fullerene, as it is like tube. So there is ending is like fullerene, but graphite like tubes. Along the axis, these nanotubes are stronger than steel and conduct electricity. As it is tube shape, that means it is, if you consider vertically along the axis, these nanotubes are stronger even than steel, and they can conduct electricity. They have many applications in nanoscale electronics, catalysis, polymers, medicine. Now coke is under amorphous form. It is not crystalline. It is hard grayish black solid containing 80 to 85% carbon. It is a product of destructive distillation in which coal is heated in absence of air. In absence of air is required, because if it is heated in presence of air, there is a chance of formation of carbon dioxide or monoxide, that is oxides of carbon, but that we don't want. So that is why in absence of air. Application is as a fuel reducing agent also. So coke is a very good reducing agent. because it itself can be oxidized to CO and CO2. That means it can donate electron towards other species. And it is used as a reducing agent in smelting iron ore in a blast furnace. That is basically application in metallurgy. Then carbon black, which is also another amorphous crystalline. Carbon black, it is also called as lamp black. It is basically the soot which can be produced. That is a powder-like black colored powder-like appearance. It can be produced when hydrocarbon, which is rich in carbon, because there may be different types of hydrocarbons. Sometimes it is rich in carbon, sometimes it is rich in hydrogen. So hydrocarbons which are rich in carbon, such as kerosene oil, petroleum, acetylene, etc. Because remember, acetylene is type of alkyne, and in alkyne we know, because of unsaturation, the number of carbon compared to hydrogen, and if you compare the same thing in alkane, obviously here it is high. That means high carbon content. So when this type of hydrocarbons are burned in limited supply of air, always it is mentioned limited supply or in absence of air, it is because oxygen we do not want. Otherwise there is a chance of formation of CO or CO2. Limited supply of air, and subsequent residue is deposited on blankets in a room, on wet blanket, because the process when it is burned, then the subsequent residue, that is in still hot condition, but if it is in touch of a wet blanket, there is a deposition. Soot can also be produced by burning of multitude of other fuels such as fats, paraffin, resins. Then industrially it is produced from gas or oil, and that is called carbon black. So this is basically the industrial name, but otherwise it is same, because carbon black used synonymously, both are having same percentage of carbon, 98 to 99%. Application is in protective coating, plastics and resistors for electronic circuits. So in the previous slide, we have seen one crystalline allotrope, which is CNT, carbon nanotube, then coke and carbon black. Now charcoal, this is also amorphous, under amorphous category. There is basically different types of charcoal possible, and that depends on from which source you are basically making it. So if it is, we are calling it wood charcoal, if we are producing it from wood. So we are heating wood, strong heating basically, again in a limited supply of air. Then animal charcoal, which is also known as bone black, it is obtained by destructive distillation of bones. Then the third type is sugar charcoal. Now sugar charcoal is pure form of amorphous carbon. That is under amorphous allotrope category if we consider. Then this one is the purest form. How we can obtain it? We have to treat sucrose or cane sugar with concentrated H2SO4, and then there will be formation of sugar charcoal. Now all these forms of charcoal, whether it is wood, animal or sugar, all of them are highly porous substance, and they can absorb many times their own volume of gases. So because of this porous nature, there is some holes inside or some tunnel-like appearance. So this can be, these vacant spaces, it can absorb many times their own volume of gases. Now this absorption capacity we can further increase. How? We can increase it by removing some impurity which is present in the walls of these pores. So in the walls, if there is some impurity, there will be some blockage. So if we can somehow remove these impurities, the vacant space will increase, so it can absorb more volume of gases. So how we can absorb this capacity, increase this absorption capacity? By heating this charcoal at high temperature 1273 Kelvin in a current of superheated steam, as the impurities are removed. So this is the purpose. We are basically removing the impurities so that more space is generated. Now charcoal which is treated in this way, that is at high temperature we are heating it, it is called activated charcoal. So activated charcoal, it is always having higher absorption capacity compared to normal charcoal, where no impurities are sticking on the surface, present. Okay. Application of charcoal. Now it has many applications. Some of these application probably you have seen also. In restaurant for cooking, heating, and adding flavors, that is some for the generation of some smoky flavor in food. As an absorbent for removing several harmful toxins. So it has this adsorption capacity which is used for removing several harmful toxins. Then in emergency medical conditions like the treatment of overdose or poisoning. So if there is some poisoning, if we are taking it internally, then it can absorb the poison in the stomach. Okay. To assist the kidney function by filtering toxic chemicals. So the holes that is present in its surface, there are some chemicals also can be it can be present, that is it can absorb these toxic chemicals, okay, as a natural water filter. So whatever this last applications you are seeing, these 3 to 4 points, all are basically related to its because of this particular type of structure, that is porous wall present. So that is why these type of applications are possible. Okay. So once we have finished the allotropic forms of carbon, there is also some other allotropes for the other elements. And other elements means the next element is silicon. After silicon, there is germanium and then tin. After tin, there is lead, but for lead, there is no allotropic forms possible. So for silicon, it has variety of different allotropes, but we will focus only on two most common allotropes of silicon. One is amorphous silicon, which is denoted like this, A-A silicon, Si, and crystalline silicon, that is C-Si, okay. The crystalline allotrope, it is gray in color, and there is some metallic luster. And what about the amorphous form? The amorphous form, that is the ASI, that is its appearance is brown powder because it is amorphous, so it is powder and also brown color. Next element, germanium. Here also two allotropic forms. One is alpha germanium like this. Another one is beta germanium. Now if we consider standard condition, then which form is prevalent? Then alpha germanium is prevalent. It has some similarity in structure with diamond, and there is some metallic luster also. But if you change the standard condition, if you change the pressure above 120 kilowatt, then it will be converted to beta germanium. Now remembering these conditions, which condition? Where allotropic transformations are occurring. So alpha germanium is converted to beta germanium when the pressure is greater than 120 kilobar. So this type of conditions, it is important as for to remember to solve different problems. Fine. Then what about tin? The next element, Sn. Here also two allotropes. One allotrope is alpha tin. It is also called gray tin because of its color. Now it is brittle in nature, cubic crystal structure. And the other form, beta tin, it is white and it is ductile. That means it is like metals, ductile properties there, tetragonal structure. Now generally, that is under normal condition, it is the beta tin form which is common. Just like in case of germanium, you have seen that germanium exists as alpha germanium under standard condition, but in this case beta tin, that is the white tin which is having ductility property, this allotrope is mainly existing under normal condition. But suppose you are changing the temperature below 13.25 degrees. See, if the temperature is very low, now beta tin will be converted to alpha tin. That means from ductile nature, now there will be some brittle nature. So what happens when temperature is very low, suppose 10 degree temperature, then because of this type of change in form from ductile to brittle nature, it is converted to some powder form. So suppose in one condition greater than 13 degree, it is like metal, then suddenly the temperature goes below this temperature, then suddenly it will be converted to powder form. Okay. It is basically known as teen plug. We'll also discuss a problem on this. Here we have a problem, assertion reason type, and this is related to diamond. So assertion is saying that diamond is good conductor of heat, and reason is saying that carbon atoms are very closely packed in diamond. Now, when we are talking about conduction, two things are there. One is electric conductivity or thermal conductivity, two types. Now, in case of diamond, there is no free electron, so electronic conductivity is absent, but thermal conductivity is very good. It is so good that sometimes it is better than normal metals. We know metals are having very good thermal conductivity, but diamond, even it is covalent compound, but still there is very good thermal conductivity property. And thermal conductivity property will be good when the structure is very rigid and tight structure. In during the discussion of diamond's features in the last class, there it is mentioned in detail. I'm not going into details to it because it is already discussed. I'm just saying that what is the reason behind its good thermal conductivity in a very precise way. It is because of its rigid structure. Then only the thermal vibration it can pass from one region to another region. Okay. So if you want to go into the details, it is not very, there is some higher level discussion is related to it, which is basically based on phonon scattering. But we are not going into the details. Just remember, when there is closely packed rigid type of structure, then only this thermal conductivity will be very good. So the reason behind their good that they are good conductor of heat, it is basically their rigid structure. That is another way of saying very closely packed structure. So both these statements are true, and they are not just true. The second statement, that is reason statement, that is actually the correct explanation of the first statement, that is assertion. So that is why first option, both A and are true, R is correct explanation of A. This is actually the correct option. The CC bond length is maximum in which of these allotropes? We have here options graphite, C70, C60. Now these two are basically fullerene, right? And diamond. Now remember, in diamond, carbons, they are sp3 hybridized, right? Each carbon, it is tetrahedrally surrounded. That is, the environment surrounding carbon is tetrahedral. What about fullerene? In case of fullerene, C70 and C60, there is different types of fullerene, but we have focused only on C60 fullerene, and there we have seen both double bonds and single bonds are present. What about graphite? In case of graphite, there is also pi bond and sigma bonds, and the bond length is there is some similarity with benzene. It is in between double bond and single bond. Now, only in case of diamond, there is no pi bond. There is pure CC sigma bond. That means only single bond is present. And when single bond is there, just I am writing here CC single bond, CC double bond, CC triple bond. So depending on what type of bonds are present. So when it is CC single bond, it is basically 1.54 angstrom. When it is CC double bond, it is 1.34. And when it is CC triple bond, it is 1.2. That means this is maximum. When bond order is increasing, that is from 1, here it is 1, bond order is increasing, 1, 2, 2, 2, 3. So when bond order is increasing, basically length is decreasing. So we have to find in which case CC bond length it is single bond, then in that case only it will be maximum. So in diamond, it is basically maximum. So here you can see all the values in picometer unit. In diamond, it is sp3 hybridization. There is no CC double bond, only single bond. It is 154 picometer. In case of graphite, it is 141.5. If you consider in angstrom, it will be 1.42 like this. So it is not exactly double, it is not exactly single, it is something in between. And in case of fullerene, there is different varieties basically. So 138, 143, two different types of bond lengths are there. And for C70, there is any variety of bond lengths. We don't need details. But remember, only in case of diamond, the bond length is maximum. Next problem. So this problem is basically allotropes of tin, that is based on the allotropes of tin. The soldiers of Napoleon army, while at Alps during freezing winter, suffered a serious problem as regards to the tin buttons of their uniform. So tin buttons present in uniform means what? It is obviously the metallic form, that is the ductile form, right? Which form is? It is the beta tin form, that is a white form. Now this white metallic tin buttons, which is nothing but the beta form, got converted under this freezing winter condition to the grey powder form, which is nothing but alpha SM. So this transformation, that is why the buttons are suddenly converted to grey powder. This transformation is related to which of these statement? The first one is saying that an interaction with water vapor contained in humid air, but it is not humid air, it is freezing winter. And even if it is humid air, then also it has nothing to do with this conversion. Okay, it is purely related to low temperature. Change in crystalline structure of tin, then change in the partial pressure of O2 in air, and an interaction with nitrogen of air at low temperature. Now at low temperature, nitrogen, obviously it is highly unreactive molecule. There is triple bond present between two atoms. It is not so reactive, and at low temperature, no reaction you can expect. So it will be anything between these two, but it is not for partial pressure of O2. We have already seen the reason that alpha form, beta form, these two can be converted to each other, and that depends on temperature. So the beta tin form, which is the ductile form or a metallic form, it is converted to alpha tin form when temperature is below this value. Now this process is basically allotropic transformation, which is autocatalytic. We don't have to add anything else of this element tin, and there is deterioration of tin objects. So just here you can see the tin object is tin button of the uniform. So it is not just for button, it is true for any metallic tin. If it is at low temperature, there will be deterioration of this white tin form. And this is known as, there is different name for it, tin paste, tin disease, or tin plaque. Okay. So B will be the correct answer. That is the change in its structure. B option is the correct. Now we will start some important compounds of carbon and silicon. So under important compounds of carbon, we have two compounds. One is carbon monoxide, CO. Another one is CO2. And when it is silicon, there is actually many compounds that we are going to discuss. Silicon dioxide, silicon carbide. So these two we have here pictured, though separate discussion will be there once we finish carbon monoxide and dioxide. Then we'll start the silicon compounds, but here we have just you can have some primary idea about their structure. So all these structures are not so simple, very large networks type of structure you can see. So silicon dioxide, the first one, then this one is silicon carbide, that is the second one. Then we have silicon tetrachloride. Now this is simpler, SiCl4, and then we have silicons. As you can see, some alkyl groups are also there attached to silicon. Then we have silicate and zeolite. So silicate, as you can see, there is only one structure is there, but it is not limited to one structure. There is so many different types of structure, so many varieties are there, and we'll see that under the heading of silicate separately, not into discuss. And what about zeolite? Zeolite is also very large network type of structure. Okay, so 1, 2, 3, 4, 5, 6, total 6 important compounds of silicon we are going to discuss, but not into this class. Today we will start with carbon monoxide. Carbon monoxide, that is CO. There is two important oxides of carbon, CO and CO2. There is another one also, C3O2 suboxide, but our discussion will be only for CO and CO2. First, we will see how we can prepare this compound, and the preparation method. The first method, as you can see, it is direct oxidation. Direct oxidation means we'll simply take carbon and we'll oxidize it with oxygen. But remember, it should be limited amount of oxygen or limited amount of air. Why we are saying so? Because we don't want the formation of CO2. If you have taken enough amount of oxygen, that is stoichiometry with respect to carbon. If oxygen is very high, then there will be formation of CO2, but that we do not want. We want to prepare CO only. So that is why limited amount of oxygen or air. Then only we can get carbon monoxide from this reaction. If we want to prepare CO in laboratory, that is small scale preparation, then pure CO can be obtained by dehydration of formic acid, and the dehydrating agent is concentrated H2SO4. Temperature is 300 degrees centigrade. So ACOH, if we remove 2H and 1 oxygen, that is nothing but water, then CO will be left. Now the third method, it is actually not directly you will get CO, but it is a mixture where CO is also present. And this gas mixture is called water gas. In hydrogen chapter also we have seen this water gas. It is commercially produced by passing steam, that is water, over red hot coke. So this is red hot coke. So temperature is high, this is steam. Now a mixture of CO and hydrogen will be produced, which is actually known as water gas. Another name for this gas is synthesis gas. In short, we also call it syn gas. Now, just like this gas mixture of CO and H2, there is another gas mixture where instead of hydrogen, now we will have nitrogen, and that is known as producer gas. Now, instead of using water, suppose you are not using H2 in the same reaction as you have seen here. Now you are using air, and air is nothing but mixture of oxygen and nitrogen. So if you are doing the same reaction but not in presence of steam, but you are doing it now in presence of air, then CO obviously will produce, but it will also contain N2 gas, nitrogen gas, and mixture of these two, that is known as producer gas. Okay. Now from this producer gas, if we want to remove the nitrogen part, or you can say if we want to get only the carbon monoxide, that is the separation of CO from this mixture, then what we have to do, the gas is passed through a solution of copper 1 chloride. Copper 1 chloride is cuprous chloride, where oxidation state of copper is +1. Cupric chloride is COCl2, or oxidation state is +2. So try to understand the difference. It is copper 1 chloride. And after absorbing this CO under pressure, there will be compound like this, CuCl, in bracket we have written CO dot 2H2. And once this complex is produced, now the pressure is reduced and this solution will release pure CO. So we are basically using copper 1 chloride to remove this CO part. So first this CO will react with CuCl, and once we are getting it, now we will decrease the pressure so that from solution pure CO is released. Fine. Now these two gases are actually very important industrial fuels. So you can consider it as if an application of CO also, because in these two gas mixture there is presence of CO, and this CO can undergo further combustion and it can produce CO2 because it is a lower oxide of carbon. The higher oxide CO2 can be produced if you are treating it with further oxygen. So further combustion possible, it will form CO2 and there is liberation of heat. So this heat we can utilize for different purpose. That is why it is industrial fuel, these two gas, because it is containing CO and CO can be converted to CO2. This is the reason. So these are the preparation methods. There is another way also we can produce carbon monoxide. which is not very important, but one time there is a question related to this, and that is, if you heat nickel CO whole 4 complex nickel tetracarbonyl, then this nickel part is removed and 4 CO molecules will be generated. Now it occurs at temperature around 450 to 470 Kelvin. Okay, this is the second step of Mons process. Mons process is actually for formation of nickel, but in Mons process, when we get pure nickel, then side product is also pure CO. So this reaction is another way to produce pure CO, but this method is mainly applicable for nickel. Here CO is the side product. Okay, so that is why we have not discussed it, but this can also be the source of pure CO. Next, we'll see the structure of carbon monoxide. Though it is a very simple, that is very small molecule, only 2 elements are there. But remember, its structural features are very interesting because there are total 3 types of bonds present between carbon and oxygen. Linear structure. This molecule has linear structure, and hybridization for both these elements, carbon and oxygen, both are sp. Now, how these sp or hybrid orbitals will be used? Just have a look. So suppose for carbon, if it is sp means 2 1s 1p mixed together, there is formation of 2sp, and other p orbital, other 2p orbitals that are still unused, that is unhybridized. So this is for carbon. What about oxygen? This is also sp hybridized. So there is 2 sp hybrid orbital, 2 pure p orbital. Okay. Now in this case, if we write the electrons, then carbon, it will have 1 sp it will use for sigma bond formation. Another sp it will contain lone pair. Now the third one, that is pure p, there will be 1 electron. Now see, 4 electrons I have already written. So that is why all the valence electrons used up. Now in case of oxygen, it is Na2s2 2p4. That means total 6 electrons we have to consider. So in sp there is 1 electron. Another sp is containing lone pair. Then the third, that is the unhybridized p orbital, there is 1 electron. See, 4 electrons, 2 more electrons are there. Here another pair of electron. Now see what will happen. These two together will form a sigma bond. This is lone pair of carbon. This is lone pair of oxygen. These two together, that is pure p orbital, one is from carbon, another one is from oxygen, it will form pi. What about the last one? Because in last case p is vacant for carbon, and here we have a pair of electrons. Now both these electrons will be donated to this, and this is basically coordinate bond, where both the electrons are coming from same element and going towards carbon. And these type of bonds are also denoted sometimes by arrow sign. So arrow will be from oxygen towards carbon. And once the electrons are donated from oxygen to carbon, after that they will behave as if it is a covalent bond. So that is the feature of coordination bond. So why I was saying that the features are important, because see, the 3 bonds present between carbon and oxygen, one bond is sigma, another one is pi, third one is coordinate. 1 sp orbital, hybrid orbital of each carbon and oxygen overlap with each other to form a CO sigma bond, as you can see here. Then the other sp orbital on each carbon and oxygen, they will accommodate the lone pair. That also you have just seen. Now the 2 unhybridized p orbital for carbon and oxygen atoms, it will form p pi bond. 2 unhybridized means one is coming from carbon, another one is coming from oxygen, not that is 2 of carbon. One is from carbon, another one is from oxygen. That is forming the pi bond. So this one, this is pi bond, this is sigma bond, this is coordinate bond, and these two are lone pair. Now look at this structure. Here you will be able to understand. The blue electrons are electrons of oxygen. Total blue electrons 6. The black ones are for carbon. Total 4. Right? So this bond is coordinate bond. Just compare with the second structure. The arrow sign is from oxygen towards carbon. And this is one is pi, another one is sigma. Suppose this is sigma, this is pi. This is lone pair. This is lone pair. Okay. Now if we consider its resonance structure, it will be something like this. Basically, this form is actually written in this way. So why, if you are thinking why there is negative charge and positive charge, it is because in the third bond, that is a coordinate bond, oxygen has donated electron towards carbon. So that is why there is negative charge over carbon and positive charge over oxygen. So this is when during drawing resonance structure, we have to write it in this way. And the other two structures, if you see, here we have 2 bonds only. So that is why there is one more lone pair present over oxygen. And in the third structure, which is the most unstable structure, among these 3 resonance structure, the third one is most unstable. Here we have, though there is negative charge over oxygen, which is electronegative, and another, as there is only one bond, so one more lone pair is there, total 3. So though it is electronegative and it is containing negative charge, but this is the most stable resonance structure, because if we consider the resonance condition, that is how to choose which structure is resonance structure is most stable, the first and foremost thing that you have to consider that structure where octet is complete and maximum number of covalent bonds are present. So only in the first resonance structure maximum number of covalent bonds are present, total 3. And though oxygen is carrying positive charge, but surrounding oxygen, 3 bonds means in this side total 6 electrons, other side 2 electrons. So octet is complete. Also true for carbon. Octet is complete. So that is why this structure is most stable, though oxygen is carrying positive charge, but that factor is not important when you consider the most, when you choose the most stable resonance structure. Okay, so this is the most stable. And because of this type of resonance, what happens? The carbon-oxygen bond length, it is 1.128 angstrom, and this is corresponding to carbon-oxygen triple bond. So this bond, experimental value of carbon-oxygen bond length, this is the proof that it is mainly existing in this structure, that is a triple bond. So whenever you are drawing CO, if you are drawing it like this, it's fine, but if you are drawing with bonds, better you always write this structure. You can also put an arrow here. So we should put it, we should draw it like this, not the other 2 structures, because this structure is most stable. And here one more important property of CO is that it can act as Lewis base. Why? It can act as Lewis base because of this lone pair that is present over carbon. So these lone pairs, it can be donated. And when it forms complex with metals, mainly the transition metals, that is nickel, copper, like this. So metal carbonyl complexes, there are many different types. So when it forms complexes with metal, just take example of nickel, then it will always form bond with the carbon side, not to the oxygen side. So if you are thinking that oxygen is having lone pairs with tendency to donate electron towards metal, it will be more. So don't think the structure is like this. It is completely wrong. This one is the correct. It is connected to all the metals. Whenever it is forming metal carbonyl complexes, it is always through the carbon side. Detailed reason, if you want to know, you have to consider molecular orbital, but that will be for higher level, not in this level. But remember, it is always through carbon, and because of this lone pair over carbon, it is also considered as Lewis base. So properties of carbon monoxide, it acts as Lewis base or a ligand. That means it can also act as ligand. The reason is same. There also you will see it is towards, that is through the carbon side, not through the oxygen side. And it can form coordinate bond with metals when they are forming metal carbonyls. So metal carbonyl, in general I am writing capital M. So here what happens, carbon donated donates electron towards metal. So that is why it is coordinate bond. The dipole moment of carbon monoxide is very low due to back donation of a pair of electron. If you simply consider carbon and oxygen, suppose all these three bonds, if it is equal contribution, suppose carbon is also donated one electron and oxygen is also donated one electron from its this side, then oxygen is more electronegative. So what we think that the negative charge will be towards oxygen. So that is why it will be polar. But remember, though oxygen is more electronegative, but as it has donated electron, so because of that reason, what happens? Ultimately, there is some negative charge over carbon. So though oxygen is more electronegative, but because of this donation during coordinate bond formation, ultimately what happens? Dipole moment will be very low because of this back donation during coordinate bond formation, from the more electronegative oxygen to the less electronegative carbon. So some negative charge over oxygen is reduced in this way. As a result, dipole moment will decrease. It is colorless, odorless gas. Water solubility is not good. It is neutral oxide. If you consider CO2, that is another oxide of carbon, that oxide is acidic in nature, but this one is not. That is an important difference. So when it reacts with water, it displays neither the acidic properties nor the basic properties. It is neutral. So there are different types of oxide. Remember, acidic oxide, which is mainly you get from metals. There is basic oxide. Acidic oxide we get from non-metals, not metals. Basic oxide we get from metals. Then there is amphoteric oxide, which can react with both acid and bases. And there is also neutral oxide, which reacts with nothing, nor that is not acid or base. So this is neutral oxide type. It has some poisonous effect. Now it is because it can complex with hemoglobin. It is highly poisonous in nature due to its ability to form complex with hemoglobin, which we denote like this, Hb. Now, it is true that hemoglobin can also form complex with oxygen. But when hemoglobin form complex with oxygen and when Hb form complex with CO, though both are fine, both formation of both possible. But in case of HbCO, it is 300 times more stable than the HbO2 complex, that is oxygen hemoglobin complex, formed in the lungs. Now under normal condition in air, there is no CO, otherwise we cannot survive. There is oxygen and hemoglobin, it is transferred throughout our body. It is because of this HbO2 complex. So this complex formation is very important for all these biological processes. But if we are in contact with CO, we are inhaling it, what will happen in the lungs? This 3 times more stronger HbCO complex will be formed rather than HbO2 complex. Now as a result, oxygen will not be transported throughout and inside our body, and as a result we can die. So this inhibits the hemoglobin present in the red blood corpuscles, red blood cell, from carrying the oxygen from the lungs all over the body, ultimately causing death. So here you can see the two reactions. Hb with O2, that is hemoglobin, HbO2 Kc value, that is equilibrium constant if you consider, it is 1.8, but this is 306. So very, very high compared to this. So this complex is very stable. So because of this reaction, it is poisonous. But this type of poisonous effect is not present in case of the other oxide, carbon dioxide, that is harmless. Now, chemical properties, reaction with air. In air, there is oxygen, so it will react with oxygen and it will form CO2, and it burns with a blue flame. Now, sometimes why it is important to remember, suppose you are getting a question where it is mentioned that a gas, that is an unknown gas, it is burning in air with a blue flame. So this indicates, I'm not saying that this is the only gas which burns with blue flame, but this is also a type of indication that it may be CO. Okay, so this is important feature, it burns with blue flame. Reaction with chlorine. When carbon monoxide is treated with chlorine gas in presence of sunlight, it forms a poisonous gas which is called phosgene. It is carbonyl chloride, COCl2. it has reducing property, because in CO, if you compare with CO2, in CO2 it is +4 oxidation state, but here it is +2. So it can increase its oxidation state by donating electron to some other species. It is powerful reducing agent, and this reducing property of CO is utilized in metallurgy. It can reduce many different types of metal oxides and convert it to their metallic form. So here we have taken zinc oxide, copper oxide, Fe2O3, iron, zinc, copper, all these three oxides you can see, and CO is reducing them. So zinc, here it is +2 state, now it is converted to 0 state, and CO, it is itself oxidized to CO2. More oxygen is added, oxidation state is also increased. Here it is 0, here it is +2. Similarly, here it is +3, it is converted to 0. So it is powerful reducing agent, but that is not possible in case of CO2. So each time any feature I am mentioning, I am also comparing with CO2 so that you can understand the difference between these two oxides. Treatment of Solene iodine pentoxide, that is I2O5. It is like this. Oxidation state of iodine is +5. This is the structure of iodine pentoxide. Solid iodine pentoxide, when treated with CO gas in presence of air, it gives CO2. And here I2O5, now we are getting iodine gas. It is in elemental form. Sorry, not iodine gas, solid iodine. Iodine is not gas. That is under normal condition. It is solid. So this reaction, it has some application. It can be used for quantitative as well as qualitative determination of CO gas, because there will be some visual change. Why qualitative? When you are getting in the product side iodine, it has specific color, violet type of, purple violet type of color. So from that we can understand, yes, I2O5 is this unknown solid is this gas is unknown gas is carbon monoxide. This is a proof. And also for quantitative purpose, because here 1 mole of I2O5, that is reacting with 5 moles of CO. So if you and in this side, if you know the amount of iodine, then the amount of CO will be 5 times high, right? So from mole ratio, we can also determine the in a quantitative manner. Metal carbonyl complex formation, as I have mentioned, there is a lone pair present over carbon, so it can donate electron from the carbon side, and it can form many different types of carbonyl complexes. Why carbonyl? Because this CO unit. So CO forms numerous complex compounds with transition metals, and you will see when it is forming compound, the metals are in 0 oxidation state, and CO itself is neutral ligand. It is not containing any negative charge. It is true there is a lone pair, but it is not containing negative charge. So metals in the metal carbonyl complexes, just take the example of nickel tetracarbonyl. Nickel is 0 oxidation state. Overall, the molecule is neutral. How we can get it? These compounds are obtained if you are heating the metals with CO. Here we will see two examples. Nickel tetracarbonyl, NiCO4, 0 oxidation state. This is also 0. And iron pentacarbonyl. Here 5 CO surrounding iron. Then chromium hexacarbonyl, 6 CO surrounding Cr. So nickel, we are treating it with CO, we are getting nickel tetracarbonyl. Similarly, iron is treated with CO, we are getting iron pentacarbonyl. Similarly, we can also do the same reaction with chromium. Fischer-Tropsch synthesis. So this process is a catalytic chemical reaction. So what we are doing in this process, we have taken CO, we have taken H2, but these two, when we are treating it with them with each other, there is a specific ratio. See, when n moles of CO you have taken with 2n plus 1 number moles of H2, which is, it is nothing but syngas. It is converted to saturated and unsaturated hydrocarbons. So though it is syngas, but mole ratio different. Here it is n, it is 2n plus 1. what you are getting? You are getting hydrocarbon, but this is CnH2n plus 2. So you can find similarity with alkane, because in alkane, this is the number of carbon and hydrogen. Okay. So now, what about if you change the mole ratio from 2n plus 1 to 2n hydrogen, that is double number of hydrogen, now it will be CnH2n. CnH2n, suppose n is 2, so it is C2H4. So C2H4 it is ethylene, that is H2C double bond. So now it is unsaturated. This is saturated, this is unsaturated, and pressure is lesser than 50 atmosphere. And there is some use of metal catalyst, temperature is in this range. So this process is where we are synthesizing some hydrocarbon, both saturated or unsaturated. This synthesis of hydrocarbons known as Fischer-Tropsch synthesis, where we are using this thin gas mixture of CO and H2, but mole ratio will be different depending on what you are trying to make, saturated or unsaturated hydrocarbon. Absorption, it is readily absorbed by a solution of CuCl in concentrated HCl or ammonia. Remember, we have in the preparation section, in the producer gas, when the mixture of N2 and CO is there, we have treated this with CuCl. So it is possible because it has this capacity to absorb. And why it does so? Because of formation of soluble complex. Here also CO is basically showing its Lewis basic property when it is forming complex, that is a CuCl complex. It will be better if there is presence of some acid HCl or ammonia, and CuCl it is mainly reacting with this, but ammonia is also there. So ultimately in the complex, Cu, copper with CO and NH3, and outside, because there will be, it is +1 charge. These two are neutral, but here we still have +1 charge, that is balanced by Cl-. Similarly, here also copper, it is +1. So here it is +1, 2 negative charge, that means excess 1 negative charge inside the third bracket, that is balanced by H, which is present outside. So positive part is always written first when we write the complex formula. After that, the anionic part. Just like that, here this part is positive, so it is written first, then the negative part. Okay, so this is another chemical property. Some more features we will also discuss for carbon monoxide, but we will end the session here. Thank you for listening.